is a set of all numbers that basically you can plug it in to give you an answer. Okay, all numbers will work. If it's a division problem, like when would this fail? When what's 0? The denominator. I'm just sort of clear. This you can't do. You get no answer. It's undefined, we say. This gives you an answer. It's 0. So anything that makes the numerator 0 is fine. It's the denominator that we focus on. So I'm saying that's your thought process. You want to figure out when the denominator is 0. In fact, we want it to not be 0. And so you solve by factoring. This is quick and easy. And you find that the numbers we're looking for are -1 and -4. In reality, that's the numbers we don't want. So we write it up like this. We say set of all x's such that it's not -1 or -4. So how many numbers are in the domain? Infinite number. This is every single number except for those two. So once again, if you put that the domain is x equals those two, you're just wrong. You don't get it. All right? So keep the right perspective. And by the way, if I just gave you like x squared plus 5, x plus 4, that was your function, what would the domain be? All real numbers. When you exclude something, well, you can't divide by 0, so anything that causes that. And you can't do square roots of negatives, because you get imaginary numbers, that doesn't count. But this would involve neither, so nothing gets excluded, so the domain is all the numbers. If I just gave you that expression, it's just a problem, basically. Now look at these. Here, what can you not take square root of? Negatives. 0 is okay. Square root of 0 is a number, 0. But square root of negatives gives you imaginary, which doesn't count. We want real valued functions here. Now look at this. So what we said is it can't be negative. Does that mean it must be positive? No. It just can't be negative, which means it can be positive or 0. Look, hopefully you're getting this, that here you can't let it equal 0. Here you can't let it be negative. Here, when we get to these, you can't let that expression, here, I'll do this one. Here, you can't let it be equal to 0 or less than 0, so here you just put a greater than symbol. In other words, it's the same thing except for a different symbol every time. That's the difference. And so if you put the wrong symbol, that was your whole job, was to get the symbol right. All right? So look at this. This one's kind of funny. I move the one to the other side, it becomes a negative. And then let me stop right there. If I square a number, is it true that that is always going to produce a positive result? Almost always true. A negative squared is a positive. A positive squared is a positive. But 0 is not. So this is what's always true. For sure, if you square a number, when you square a number, you never get a negative. But that means, since this result must be, well, more than negative, it must be 0 above, this statement can't fail. I mean, this is simply always true, right? For any value of a, it'll always be true. Which means there's nothing to exclude from our domain. So what is the domain of this? All real numbers. Because we're trying to figure out when you'd get, basically when would you be doing square root of a negative, and that's never going to happen. So there's nothing to exclude. So that's the thing to keep in mind here. Now I want to do this one because it's different from anything I had in the notes. Basically, you're solving a quadratic inequality. Okay, that's a different skill from solving like a linear inequality. This is much easier. You say that needs to be greater than 0, but you just solve for x. It's easy. Here, look, first of all, obviously the numbers are plus or minus 4. When I say the numbers, those are the numbers that make it equal 0. And that's what your algebra gives you, right? But what I understand is what you do with the quadratic. You get those numbers where it equals 0, and you put them on the number line, you test the intervals. Okay, that's your approach. By the way, just for the record, I said these are the numbers that make it equal 0. Do we want to equal 0? No, because if when this equals 0, you get division by 0, so it fails. I'm going to put open circles there, because those don't actually count as part of our domain. Just want to get that out of the way now. Now when I said test interval, pick a number from this middle interval. Any number will do, but I'll choose 0. And when I plug in 0 into this expression, I get a negative, yes? I'll just put that here. Now, if I pick a number from here, what do you want me to use, 5, 10, or 1,000? 1,000's easy. Clearly 1,000 squared minus 16 is positive, isn't it? Right? Obviously. It's actually 1,000,000 subtracted by 16, but it's definitely positive. And do you want a negative 5, negative 10, or negative 1,000? Or how about negative 1 billion? Negative 1 billion, right? Squared is definitely a huge positive number. And it's 1 quadrillion, yeah. Or is it? Maybe bigger than that. Or sextillion. more than likely, actually. So and we wanted to be positive. We want to be greater than 0. So that's it. The domain is all those numbers up to -4, not including -4, and from 4 on. Yes. Okay. So like I said, keep those different cases straight on that. One more on the homework. I want to go over one of these. We haven't talked about piecewise functions yet. And we'll do a lot with these, but just let me get the idea across here. Basically, you have 3 different rules that work on different parts of the domain. So you have different parts of the graph. I just want to show you what the domain is in this graph. If I put these 3 pieces of the domain together, this represents all the numbers up to -6, not including -6. So that's this first interval. The next interval is from -6, but it's inclusive. -6 to +12, including both. That's this middle interval. And the last one is from 12 on to infinity, not including the 12. Okay? What I'm saying is you put those pieces together, well, let me ask this. It goes from -infinity to +infinity, but are there actually any numbers skipped over by all that? No. -6 is part of it because it's included right there. +12 is a part of it as well. It's actually all real numbers. That's the domain of this thing. It's just been broken up into 3 different pieces. Okay? That's what you need to get about a piecewise function. That's always the case. That this is the domain broken up into pieces. Now, you didn't need to do that for this problem, but you need to get that concept that here, this is very easy. You just need to pick the right rule, and -5 is in part of which interval? The top interval or the middle interval? Is -5 less than 6 or greater than -6? It's greater than -6, yes? Which means you're supposed to use this rule on that x value. So and that's it. You just choose the right rule, and then do that math. And then you get, that's 25 minus 5 plus 1 is 21, and you're done. I'm not going to do f of 12, but which rule would I use for f of 12? The middle or the bottom? Certainly not the top. The middle, because it has the equals 12 there, not here, right? And so you actually use the same rule. You do 12 squared. If I was doing f of 13, I would use this rule. If I was doing f of -13, I use the top rule. Because, like I said, you choose based on the x value you're plugging in. Yeah, that's supposed to be holding the baskets, not her personal carrier. I don't think it has wheels. Like, she's just dragging it around. And this I always thought was amazing. Apparently, the truck got iced up. Then the guy starts his truck, lets it warms up, and so when he pulls away, that stays standing there, which is rather phenomenal, I think. Yeah. Now, look at this. I'm sorry. Yeah. Look, we're talking about functions still, obviously. That's what the whole chapter is about. One basic idea you need to get about functions is, like when I say function value, that's the y value, and we'll track the function value over time. And that's how we'll talk about it. That's how we'll describe it. And so here, the function value is a price. It gets bigger. It's increasing. It hits a maximum there. The price is decreasing. And so the function value is increasing, then decreasing, hits a minimum there, and so forth as time goes by. And so x value, even if it's not time, we kind of think of it as being time. And so graphically the same idea. As we go across, if I said, what's the maximum function value? Well, that'd be like almost 2.5. When did that happen? Well, at this time here. And so you can track the function value as you move across. We're going to skip over those. Vertical line test, you know this. Which one's a function? The one on the left is. That one fails the vertical line test. That one is also a function. That one fails the vertical line test. Which of these is a function? One left. I guess I should change it up a little bit so it's not always the one on the left, but yeah. This one fails because you're hitting 2 points, whereas this one you're not hitting 2 points. Okay? Now look at this. Talk about domain now. And I just want to show you this example. This notation, look, first of all, the domain is from -2 and below. That's -infinity to -2. And then from 2 on, right? Okay, fine. So that's interval notation, which is nice. This is set-builder notation that corresponds to that. This is what you probably haven't looked at or seen or been familiar with. It's the same thing. When you say absolute value, you're saying, how far are you away from 0? And so these numbers I shaded are the numbers that are 2 or more away from the origin. Or 2 or more away from 0. And so that's a nice, more succinct way to express that. So use that if you want to, is all I'm saying. All right, we'll do both. Here, this one, just be careful. A lot of times on this, people say the domain is -3 to 3, which is false. it's really negative infinity to 3, yes? And the range is negative infinity up to what? Another mistake people make, maybe not so much here, but especially if this endpoint was like here, they want to focus on the endpoint, when in reality, you're supposed to go from bottom to top for the range, right? So the range should have been that set of numbers, like you said. Next one. The domain is starting at -3, of course, exclusive. Is there a gap? It goes to infinity, but is there a gap in the domain? No. There is a jump in the graph, but you don't skip over any x values. Now for the y values, the range, you go from negative infinity up to -1, exclusive I said, and then 1. So it's all the numbers, all the y values here, and 1. And let's say express something like that. And it's just a set of numbers that has all those y values, and this is really a set of numbers expressed in interval notation. Union, that set of numbers that just has 1 in it, that's your set of numbers, that's your range. Okay? And so that's how you'd have to express something like that. All right, well, we can do this. We're going to go quickly through this. Like I said, about 8 minutes till the hour is when we'll start the assessment. I mean, you'll have more time to finish up your assessment. All right, first of all, you're given an x value 0, the y value is 4, yes? What's the next answer? Because the x value of 3 power 2 gives the y value 0, and the last one is here, so you got -4. The domain of this thing is easy. It just goes from 0 to 4 pi. First period, I put -4 to 4, which that was the range. So I caught myself though. The intercepts, that's easy. There's 4 x-intercepts. And when you're listing x-intercepts, you can just list the x values. The x-intercepts are power 2, 3 power 2, 5 power 2, and 7 power 2. An x-intercept is an x value when y equals 0, yes? There's only one y-intercept. And with functions, there can only be one y-intercept. So 4. What's the next question? E. What's the answer to that question? If I drew across, I hit 1, 2, 3, 4 times, right? Next one is easy. The y value -4 happens for these two x values, pi and 3 pi. The last one takes a little more thought. Look, you want your y value to be positive, not 0, not negative, but positive only. So this part of the graph has positive y values. You're supposed to be writing down the x values, though. And you can't list them. There's an infinite number. So you write it intervals. From 0 to pi over 2 is the time during which you have positive y values. Which of these actually gets included in that? The 0 or the pi over 2? Because the y value there is positive, but this y value is not. So it needs a parenthesis there. And then the next interval, and this doesn't count, then from 3 pi over 2 to 5 pi over 2. But it's 0 at both of those, so don't include either one of those. And then 7 pi over 2 to 4 pi. Do we include the 4 pi or not? Yes, because it has a positive y value. I don't know what that is, but not a bracket. Right there, fine. Okay? And we're going to skip to this example, okay? That was looking at the graph, now we have to do everything algebraically. So is this on the graph? Just find f of -1, first of all. And so plug it in, do the algebra. Notice you need parentheses around the -1, especially right here. People tend to leave it off, but it's wrong without it. The numerator is 2 times 1 is 2. The denominator is 1 plus 1, which is 2, which means you get 1, which means it's a yes. Because when we plugged in x value 1, we did get a function value 1. Next question is similar but not the same. Start out the same by plugging it in. So you get, yeah, that's right. This, you get 4 times 2 is 8 from the numerator. 16 plus 1 is 17. So as an ordered pair, it was an x value of 2, a y value of 8/17. Just don't get the order backwards when you do that. The function value is the y value. I'm going quickly, but we need to. All right, this one. Now they give you the y value, so you set the equation equal to that y value. Since the thing looks like a fraction, I mean, this is a fraction, I'm going to make that look like a fraction. It's just 1 expressed that way. And I'm going to cross multiply. I'm going to put this on the left side. This is going to be a little different. First of all, you get x squared minus 2, x power 4. All right, so this is going to be a little different. I forget it. Look, we're going to do what's called u substitution. In other words, if I call u x squared, and you can use whatever variable you want. But if u is that, then u squared is that squared. So I'm saying I'm replacing that with u, I'm replacing that with u squared. And then your factoring is much easier. That factors into that and that. You basically get u equals 1. Well, from both of them. That means x squared equals 1. I feel like I'm messing up, but I guess not. And then now, the funny thing here is, after all that, you get this, and that doesn't have any real numbers. So, it just doesn't exist. Answer is none. Because once again, if you went further with this, you get plus or minus square root of negative 1 or plus or minus I, which doesn't count. Did I mess up? Right. Oh, I should have said x squared equals 1. Sorry, I felt like something was going awry there. All right. You remember when I said I usually get my mistakes gone by now? The problem is I didn't do this example in the period, so I skipped a step. Earlier it was x squared minus 1 equals 0, which is x squared equals 1, which gets you plus or minus 1, actually. All right, fine. And then to answer the question, so that's to answer the first part. What points are on the graph? Well, these are both x values produce a y value 1. So 1 gets you 1, and negative 1 also gets you 1. All right. Now the domain of this thing. You want to figure out when the denominator is 0 because you can't let the denominator be 0, right? But the fact is, it'll never be 0. You can do this step. Move the 1 over, becomes negative. And x to the power 4 never would be negative, right? So what's the domain? All real numbers. If you find there's no way that this can fail, there's no way the denominator can be 0, then there's nothing to exclude, which means you just have everything you start with, which is all real numbers. All right, x-intercepts. How do you find an x-intercept? You set the thing equal to y by 0. Always, that's how you set y equals 0 to find x-intercepts. Listen, when does a fraction equal 0? Only when the numerator equals 0, right? So in other words, all you have to do, you can do it a harder way, but all you need to do is set the numerator equals 0, which in this case is when x is 0. Quite right. And if you plug that in, you don't get 0 in the denominator, because then it just doesn't exist. So it doesn't even exist at this x value. And so the x-intercept is 0, which, by the way, you can just leave it like that. That is the x value that made the y value 0, which means that represents the origin. Now the y-intercepts are easier. All you do is find f of 0, right? The y value is, the y-intercept's the y value you get when x is 0. And that's 2 times 0 is 0. That's 0 plus 1 is 1. So you get 0. Of course, you should have known that anyway, because the x-intercept is the origin, so that was also your y-intercept. Okay. We're going to skip over those. We need to talk about symmetry. Okay? Look, you have 3 kinds of symmetry. Okay, you can get more than these 3 kinds of symmetry, but the 3 you're responsible for is figuring out if the graph has x-axis, y-axis, or origin symmetry. So, and just to remind you, when I say line symmetry, like here, you're reflecting across that vertical line. This is a horizontal reflection, right? the point is, if you replace x with the opposite, you should get another point in the graph, if it has y-axis symmetry. The x-axis symmetry, if you replace the y with the opposite, then you should get another point in the graph. That's how you reflect across the x-axis. Origin symmetry, you switch both signs, first of all. That's what the rule says. And so if you switch both signs, you get another point in the graph every time. Then it has origin symmetry. But point symmetry is less familiar. Physically, what you do is you take the point, go through the origin, and go the same distance the other way. That's how you reflect across that point. And if you can reflect every point through the origin and hit the graph every time, then it has origin symmetry. And it does. By the way, of these three, which one could never be a function? The x-axis symmetry, right? Because by definition, that means you're going to have two different y values for one x value. And so tomorrow we'll talk about even or odd functions, which we talked about before, actually. They can't be talking about x-axis symmetry then. We're going to talk about even or odd functions because they're functions. All right, we're going to skip over this. This summarizes three rules. To check for x-axis symmetry, you replace like this. Y-axis, you replace like this. Origin, you replace both. And that's what we're going to do now. Listen to me. This is all about showing the work right. Okay? And getting the answers is, well, important. But getting the right answers with no work gets you very little credit. Okay? So I'm saying show the work properly. So watch this. For x-axis symmetry, it's vertical, so you replace y with negative y. I must see that setup. I can do this. So replace y with negative y, like I said, for testing for x-axis symmetry. Then simplify. For this, we need a couple of identities. There's, okay, that's the word identities. There's two basic identities that you need to know for this. And that is, if you had this expression, you can replace that with this. But if you had this expression, then it gets replaced with this. And understand, these get the same answer always, but they're not the same. Here, you take the opposite of your input and then cube it. Whereas here, you cube the input first and then take the opposite of that. It just turns out they get the same answer every time. But that means you can replace either one of these with what's on the right. So like here, you set it up, and then that gets replaced with just plain old y squared because you can. Okay? So like I said, you set it up, you plug in the opposite of y in place of y, you simplify, and if what you get matches what you started with, then you know it has that type of symmetry. Y-axis, you do the same thing, but now you replace x with the opposite of x, and you must put parentheses around it. Here, you kind of would anyway, but you had to have parentheses there. And obviously it works out the same way, because it's also an even exponent. That's also a yes. Now, before we do the next one, there's some rules here that you can use. You're supposed to explain yourself here, okay? So what I'm saying is, if you have x-axis and y-axis symmetry, then you will have origin symmetry. You must. If you don't, if you have one or the other, but not both, then you won't have origin symmetry. Now, it is possible that, basically, it's possible to have a graph that has no symmetry, right? Obviously. There's plenty of graphs that have no symmetry. Or if it has symmetry, it might not be one of these three types of symmetry. So I'm saying definitely these could all be no's. But I'm saying if these are no, both no, this could still work out to a yes. It just doesn't have to. All right? So I'm saying if you have this, you can conclude this. If you have either of these cases, you can conclude. And so you can write this answer without showing any work, is what I'm saying. But this, you have to show the work. Here, so I'm saying either put yes and explain in words that is yes because it had x-axis and y-axis, or justify your answer here by showing the work, which is easy. And then it just works out because it simplifies the same way. And frankly, that's probably the quickest and easiest. Just repeat yourself. I am giving the option of just explaining in words how you knew that. Okay? Good? If you graph this thing, it was an ellipse, a vertical ellipse centered at the origin. So that's why it has all three kinds of symmetry. All right, let's try the next one. X-axis first. For that, I replace what? Y with negative y. Once again, you must show proper notation there. If I don't see parentheses, you don't know what you're doing, and you get it wrong. Now this, when you simplify it, becomes the opposite of y cubed, but it didn't start out that way, so I need to see this set it properly. Does this match the original? No, so it does not have that kind of symmetry. For the next one, you replace x with negative x. Now, as far as showing that, you don't really need parentheses there. I mean, it's just an x sitting there. So if you just replace the x with negative x in one step, I'm okay with that. And that's also no, because it does not match exactly. All right, the last one, you replace both. X gets replaced with negative x, y gets replaced with negative y. Bring this down. That gets replaced with something similar, but without parentheses. We are simplifying there. It just looks very similar, but it's different. Now listen, it doesn't look like the original yet. But this one actually can. What you can do is just divide everything by -1, or just switch every sign. You don't have to show the work even. That becomes a positive. That becomes a positive as well. And that's still 0. So it's yes, except for that wasn't squared. Okay? If this had not been a 0, then it would not have worked out, I'll just tell you. But it does. Watch this. If I graph this thing, I could either write this as x equals negative y cubed, or I could also write it as y equals negative cube root of x. It's a cube root function. But it's flipped vertically. And so it does have origin symmetry. And look at it. If I try to reflect it across the x-axis, take this point and reflect across, there's nothing there. It doesn't have x-axis symmetry. Reflect across this way, it doesn't have y-axis symmetry, right? It just has origin symmetry. All right. We're going to stop there. We'll finish it tomorrow.